welcome to the first plenary session of this year's Korean Astronomical Society 4 meeting. My name is Sasha Tuppe. I'm of Seoul National University. I'm going to be the chair for the first plenary talk. Well, it's my pleasure to introduce Professor Kyu-Hyun of Sejong University, who is going to talk about a specific test of gravitational dynamics. Well, everybody knows about dark matter. Not everybody knows about that other explanations for the missing mass problem exist, that a specific modification of gravitational dynamics might just possibly even provide a better explanation. And Professor Chae today is going to talk about a specific observational test that might distinguish these various scenarios. Please go ahead.
Hello, Sasha, thanks very much. Hello everyone, and thank you very much. It's a great pleasure to talk about these interesting results. So I have 30 minutes, so I will start now. Okay, so this is the outline of the talk. What are the motivations, and I'm going to describe the database, and also I'll try to point out the main idea of this method, and I'll present the results with some discussion, and I'll give a conclusion and the future prospect. Okay, the outstanding unsolved problem in astrophysics: what causes gravitational anomalies at low accelerations in galaxies and galaxy clusters? Here, less than 1 nanometer per second squared. So it's either dark matter or breakdown of standard gravity, right? So there has been no direct detection of dark matter so far. Also, there are growing challenges to standard cosmology based on general relativity and dark matter and dark energy. And there are many reviews. This is one of them. Okay, so what does the breakdown of standard gravity mean in the context of DM problem? Because anomalies occur at low acceleration, it has nothing to do with relativity. So it means breakdown of Newtonian dynamics regardless of relativity. Okay, that's why it is called modified Newtonian dynamics. It was first proposed by Morda and Milgrom 40 years ago. Because general relativity approaches Newton's gravity in the non-relativistic limit, the anomalies mean a breakdown of general relativity. That's why it is a very, very big deal. Okay. The question is, can one directly and conclusively test the low acceleration breakdown of standard gravity? Okay, this is the question. Here, the point is directly and conclusively. Okay, indirect and circumstantial arguments are not convincing. So there have been those arguments for many decades, but no one is actually no one is convinced. Okay, so in galaxies, one needs to distinguish between the predictions of dark matter halos and the MOND. Okay, this is one example. And the main thing about dark matter is that the required amount of dark matter in galaxies is considered to be reasonable, compatible with the cosmological argument. Okay. So here I'm going to talk about two observational proposals. One is if we can find a perfect correlation between external field effects in galaxies and the directly measured external fields from the environment, then that will give direct evidence for MOND. Okay, and this is the work I'm involved with these people. And another thing is testing gravity with wide binaries. Wide binaries means widely separated long period binaries. That's why it can reach a low acceleration regime. And the effect of hypothetical dark matter, even if it exists, are negligible. So it provides a really direct test of low acceleration gravity. Okay, and this is the topic of this work. Okay, so MOND prediction is that there's a transition range. So it will be Newtonian, but it will be Mondian at low acceleration. So in terms of typical wide binaries, it occurs between about 10,000 astronomical units to about 8,000 astronomical units. So the transition separation would be around 2,000 or 3,000 astronomical units. Okay, and the period is given here. So it can reach from 10,000 to a few million years, the period. Okay, this is an example of a MOND-type modified gravity. It's nearly 40 years ago. It's a modified Poisson equation. It's called the AQUAR. And it has this typical characteristic of this interpolating function. So when x is much larger than 1, it approaches Newtonian. But when x is less than 1, it becomes Mondian. Okay, and the characteristic acceleration is around 0.1 nanometer per second squared. Okay, so what this theory predicts? Okay, here there's one important complication. That's the external field effect from the galaxy. So around in the solar neighborhood, the external field of a galaxy is rather strong in this context. So one has to take into account the external field of effect of the Milky Way. And then if once is taken into account, the prediction is like this. So this is for circular orbit. So for Newtonian, the Newtonian acceleration and observed acceleration will be one-to-one correspondence. But what this theory predicts is that it will shift to this Mondian region, and actually it becomes Newtonian. So I'll call it pseudo-Newtonian, because it is essentially the same as Newtonian with a slightly rescaled Newton's constant. That's why it's confusing to how to test this regime. In reality, it becomes more complex due to eccentricity. Due to eccentricity, the median relation goes below this circular line, even without any gravity effect. So the actual curve will be like this. And what MOND predicts is like this red curve. But the difference will be similar, okay? Okay, what this work is not about, this work does not test any dark matter models, because even if it exists, it cannot affect binary internal dynamics. Okay, also this work does not test any cosmological models. Okay, because you know how these binaries were formed are not important for this test, because we have observed the binaries and then we are just testing its gravity. Okay, so what are the Gaia data I'm using? Gaia is constructing 3D map of 2 billion objects in our galaxy. And we have Gaia data release 3, okay? And it provides proper motions, also radial velocities. Okay, so proper motions and accurate parallaxes gives sky projected velocities. And also radial velocities are not as accurate as sky projected velocities, but they also provide some important information. Okay, so the basic database I'm using is taken from El-Badr et al. So they provide 1 million binaries. Okay, so initially they select binaries. The separation is less than 1 parsec. And also the two objects have the same distance, okay? But they then undergo the process of cleaning contaminants, okay? So they remove clusters, background pairs, and resolve the triples. And this is the sample they provide. It's 1.8 million candidates. But this sample may include chance alignments, okay? They are not genuine binaries, just chance alignments. So when they have chance alignments, they will have different radial velocities and so on. Okay, so this is the initial candidate, and after cleaning, and now these people actually study chance aligned probability very carefully. And one of the main contents of the paper is about this chance alignment, El-Badr et al. So I'm taking advantage of their results. I mean, they are the best people about this study. So there's no point for anyone in the world to, use other methods, because they already did great job in calculating chance alignment probability. So once chance alignment probability is very small, then it's quite different from the cleaned sample. Actually, it is very similar to the cleaned sample for lower separation bit, but at larger separation, it becomes different. Okay, but I don't use all of the binaries they provide. I select very carefully some small sample, because I'm trying to do very accurate tests. So the basic strategy is that try to exclude false binaries as thoroughly as possible, and use the most reliable data as long as statistics is okay. And also, this is important, separation binaries to calibrate the amount of hidden close concurrence. And this is the actual key point. Okay, this shows the color magnitude diagram. Okay, and this shows the uncertainties of the sample, and this shows the uncertainties of distances, actually fractional. This is with the distance. The first one shows fractional uncertainty of distance. The second one is the fractional uncertainty of proper motions. And I'm basically using the binaries that satisfy certain criteria. Okay, these are the criteria. And I'm also taking into account dust extinction correction for these larger distance binaries. Okay. Also, 30% 37% of binaries have measured radial velocities, but it has, as you can see, the measurement uncertainties are very large, typically. So they cannot be used in general for testing gravity, but they provide the, they allow whether a binary is a true binary or not. Okay, this is a Monte Carlo test. Okay, so the sample I select whether it is a true binary sample. So I did the test with the radial velocities. So if they are true binaries, then radial velocities must agree within uncertainties, and this test shows that it is really this. Okay. Also, we need to estimate the masses of the binaries. This is the test of gravity, so we cannot use dynamics to estimate mass. So we need to estimate mass independently of dynamics. That's how we can test gravity. So actually, there are many well-respected, reliable relation, and I did very thorough test of this relation. And then also Gaia DR3 provides their masses, and they are all consistent. Okay. Now I'm going to describe the method of the analysis. Okay, the basic idea is that I define kinematic acceleration and derive kinematic acceleration through Monte Carlo deprojection of the observed proper motions, and then compare it with predicted Newtonian kinematic acceleration as a function of Newtonian gravitational acceleration. Okay, these three parameters are the key quantities you need to remember. And because the orbital period is very long, but Gaia DR3 observation is just for 3 years. So it's basically observation at an instant of time. So there's no hope to test gravity with an individual binary from Gaia. That's why we need statistical approaches. So the statistical approach is so I select bins of Gn. Okay, then in bins of Gn, you can compare distributions of G observed and G predicted. And also to get G observed, you need to do Monte Carlo projection, as I said earlier. And also we need to take into account hidden close companions statistically with a proper calibration. And this is very important. Okay, so this is the binary. Then you have two velocities, and the relative velocity is 1 meter, and we have total mass, and it can have semi-major axis, and this is the radius, physical radius, and what's observed is projected separation. And this is the definition of kinematic acceleration, and this is the definition of Newtonian acceleration. If the orbit is circular, then these two will be the same in Newtonian physics. So what Newton predicts is Keplerian orbit, okay? And it predicts VR is given by this. So we need to relate orbital motion to the proper motion, observe the proper motion. And so I define sky plane, and this is the orbital plane. So one can do the geometry, and the sky projected separation is given by, so projected velocity can be connected to physical velocity. Okay, this is some observational studies on eccentricities. So I'm using this information. And for inclination distribution in 3D geometry, this is the probability distribution. And also this angle, the orbital angle distribution is from the time distribution along the orbit. And this is the prediction of this ratio in Newtonian prediction as a function of eccentricity. So at large eccentricity, the distribution is huge. So it can be actually larger than the circular prediction, but the median monotonically decreases with eccentricity. Okay, so how to obtain G observed from proper motions? So this is the proper motion, and you get projected velocity, and then you do the Monte Carlo deprojection. So in each Monte Carlo deprojection, you take inclination and these angles at random. So one Monte Carlo data is meaningless. Okay, only statistical data can be used to test gravity. So how to obtain Gn? Gn is from the magnitude, and from magnitude to stellar masses, as I said, mass magnitude relation is very reliable, and I tested a range of, so it's quite reliable, and then so you just need to do this the deprojection of the sky projected separation to physical radius. Okay, and then this shows Monte Carlo distribution over one system. So if you do Monte Carlo deprojection, then you will take just one of the data from this possible data. Okay, so one individual system is meaningless, but if you add thousands of them, it will show some characteristic. So the statistical fluctuations will be averaged out. Okay, so the distribution or the median can be used to test gravity. Okay, so as expected, it is below the circular line because eccentricity is high. Okay, so this is one Monte Carlo result. And then if you do many Monte Carlo, then the medians will have a distribution. This is from 200 Monte Carlo. Now, how to predict this, how to get G predicted value from observed separation and magnitude that need to be compared with observed acceleration. So we can calculate this and then obtain sky projected velocities. And you just need to replace the observed proper motions with these simulated proper motions. Okay, before considering statistical analysis of accelerations, let me consider projected velocities, ignoring hidden close companions. Okay. Okay, then it is clearly higher than the Newtonian prediction at all bins. Okay, and this is the consequence of ignoring hidden close companions. So actually, apparent binaries are not actually binaries. Many of them are actually triples or even higher. Okay, so this is simply not observed because it is faint. Also, the separation is small. So we need to multiplicity fraction define, and then we need to calibrate this because this parameter has trade-off between gravity and with gravity. So it is extremely important how to treat this parameter. Okay, these are the observational information on the companions, hidden companions. Next, okay, next. Okay, so how to get Newtonian prediction, draw Mach proper motions for both outer orbit and any inner orbit, and then do the vector sum and to get the simulated net proper motions. Okay, what matters is the motion of photocenter, not barycenter, because the two stars have a different magnitude. So because what's observed is the motion of photocenter. So one need to multiply this factor. Also, this observing time is just 3 years. So it's essentially 0 for less than 3 years. Okay, so how to self-calibrate this F multi-parameter? So the basic idea is that for next, yeah. If this parameter is similar for all binaries as observation indicate, then it can be determined by requiring small separation binaries to follow Newtonian gravity. Because at this higher separation regime, there's no gravity theory, including Mond, that predict deviation. Okay, so it is very safe to require this small separation dynamics satisfy Newtonian gravity. Okay, so basically, I'm using this to self-calibrate F multi. Okay, so this process is so complex. Actually, the code itself is not so long, but the process is complex. So I actually posted code so that anyone can test and then play with it. Also, I'm updating the code whenever bugs or improvements are found. Actually, I need to confess one thing. While preparing this talk, I found a small bug. And so I was actually panicked. Nobody pointed that out to me. So I found it myself. So I was a little panicked, but when I corrected the bug, actually now the evidence is stronger. So due to the bug, actually I made my argument a little weaker, but now it seems stronger, okay? Okay, so this is the test with the Newtonian Mach data, and this is the scatter one expects. So if the gravity is Newtonian, then you expect your observed deviation can be higher or lower. Okay, it can be something like this. Now, what the results are? The results are this. Okay, this is for a smaller sample within smaller distance. And this is the Newtonian prediction, and this is the Gaia data. And they are very similar, but there are, slight difference. Okay, so the question is, what's the statistical significance of this? So I do Monte Carlo. Okay, so one can do Monte Carlo to obtain distribution of the medians. And as you see, okay, so these parameters were calibrated. Okay, that's why they are slightly different. So it's calibrated so that higher acceleration data agree with the Newtonian prediction. Then these data don't agree with the Newtonian. So here, the significance is around 3 sigma. Now I'm going to the higher sample, the main sample. And it's like this, next. Now the significance is astonishing. It's this data alone, like more than 7 sigma. Here, F multi seems a little large, but as I said, when I corrected the small bug, it's around 0.5, so it's reasonable. Next. And these are the results. So basically, the predicted the observed acceleration in the Mond regime is about 1.4 times. Yeah, next. So this is the figure I put on press release, and this is the calibration point, and then I didn't calibrate this point. I calibrated. So this is the I use 5 bins, okay, and this is the calibration point, and this is automatically satisfied, and this is non-trivial result, okay. So that means if this is Newtonian, then this is also Newtonian, but this part is clearly deviates and it agrees with Akar's prediction. It can be a coincidence. Yeah, next. And this also shows the results in 5 bins. Next. And so I did also pseudo-Newtonian simulation with this pseudo-Newtonian regime only to check. And then it shows they are agree. Here is slightly shifted, but they are actually consistent. The error bars overlap, so it's not a big deal. And if I use a little higher Newton's constants, then it can agree well. So basically this figure confirms that the data in the Mond regime is pseudo-Newtonian, okay, with the rescaled gravitational constant. Next. Okay, I did the complementary test. It's on archive and just submitted a month ago, and actually I'm working on referral report. Referral report is reasonable, okay? Now, here I try to obtain pure binaries, okay? So try to clean all systems with companions. Okay, next. So here, for this system, F mark is 0. Okay, that means that's the definition, statistical definition that the sample is statistically clean. Okay, then even in this system, you have the same result. Okay, the number is very small, but all the details are gone here because I'm removing these triples. But the results are essentially the same. Next. And if the sample doesn't contain any contaminants, then one can actually do the test with the stacked velocity profile. Okay, this was not possible when the triples are included, but one can do the test, and then it shows clearly, the higher acceleration regime agrees with the Newtonian. In this case, there is no free parameter error. There's no free parameter because masses come from magnitude, and just need to do some Monte Carlo, but there is no free parameter. Okay, then you get Newtonian result automatically, and this is non-trivial. And I mean, this shows that all the data are reasonable. Okay, but here, so the selection is the same, but here there's a clear deviation from, and it agrees with the acceleration analysis. Next, yeah, and this one is in exceptional systems, radial velocity are very accurate. So I also did this, but number is so small, so don't take it too seriously because the number is so small. So this is just test. Yeah. Okay. So why did the previous studies, for example, Pitodis and Sutherland, fail to obtain the Mond signal? Wide binary test has been around more than 10 years. The main reason is that they did not self-calibrate this FMRT because they considered only this pseudo-Newtonian regime. So that's why it is not surprising they obtained the Newtonian result because it's a Newtonian, it's a pseudo-Newtonian with the rescaled Newton's constant, but this rescaled Newton's constant can be traded off by this F multi. So one can get, so you can get Newtonian result. Also, this study include flyby cases, and then so they have another free parameter. So, but actually, this Javier Hernandez is the person who actually presented this test more than 10 years ago. He now obtains results consistent with mine. Actually, his results were a little higher than Mond prediction. So his anomalies were actually higher than Mond. So it was hard to understand by the community, but he now actually corrected his analysis. Now he says his results entirely agree with mine. Yeah, next. So these are the conclusions. So wide binary dynamics shows an immovable gravitational anomaly. So I invite you to test yourself because we are talking about science. So I'm not, trying to publish a paper. I don't need to publish a paper. Okay. So we are talking about science. So I invite the whole world to test this. That's why I put my code, on made public. So moon type modified gravity based on my test correctly predict the gravitational anomaly. And the relativistic theories need to be reformulated because general relativity approaches Poisson's equation, not modified Poisson's equation. So general relativity is actually limited. It's valid outside the Mond region, okay? And dark matter problem and standard cosmology based on it need major revision, dark matter paradigm. And it seems that a paradigm shift seems now on the way. I mean what I say, yeah. And the free-size measurements of radial velocities, so pure binaries may return fruitful results because we have very limited number of free-size radial velocity. So this is the area the measurements can be improved dramatically. And also Gaia DR4 and the later data may be useful, okay? So thank you, yeah.
Thank you very much. I'm sure we have a few minutes of time for questions. There should be plenty of questions. So, who wants to go first? Anyone? Okay, who was first? Over there, yes. Yeah, over there.
Where do your radial velocities come from?
It comes from the Gaia database. Yeah, Gaia provides their own radial velocities. The data release 3. Yeah. So Gaia data release 3 have better radial velocities than earlier data release. Yeah. And so one can maybe use some dedicated program to measure radial velocities for actually at least for some sample.
Okay, that's over there.
I do not know much about this, so I have a very simple question. What is the low acceleration gravity and how does it differ from high acceleration gravity?
Okay, so I expect most of you not familiar with Mond, okay? So that's why this question. At acceleration higher than about 10 nanometer per second square, it will be Newtonian, and then in relativistic regime it will be general relativity. now at acceleration lower than 0.1 nanometer per second squared, what this data say is that it's not Newtonian. So it's not general relativity. So there's a transition acceleration around 1 nanometer per second squared. Yeah, so above that acceleration, it will be Newtonian, and then relativistic velocities, it will be general relativity. So I'm not talking about, say, black holes, neutron stars, gravitational waves, and so on, okay? Because that's the area where motions are relativistic, so that has nothing to do with it. But general relativity need to be modified to include this movement. So, yeah.
Okay, given the time, so do we have maybe another urgent question? Yes, one question here.
So probably one of the important calibration is actually the magnet mass relation.
Yeah.
So if you have some slight systematic error of the magnet and mass relation, then what result you will get?
Actually, mass magnitude relation is not a big deal. That's because it's triples, the hidden companions, the hidden companions are so important. So compared to it, mass magnitude relation difference is minor. So if you shift mass magnitude relation slightly within some range, then it will shift F multi, multiplicity fraction. It's basically changing mass magnitude relation is about masses of stars. Okay, so it's about the total mass, but total mass can be the more important factor for total mass are hidden close companions. So mass magnitude relation is minor compared with these hidden close companions. And if you shift mass magnitude relation, then it will shift the F multi value. But in my case, F multi is free parameter, and it's calibrated. So even if the mass magnitude relation is slightly has a systematic error, but I doubt because I checked the most reliable relations, and also I checked with the experts in this field, okay, and then they consistently said the same thing. So, but even if there's some systematic shift, okay, it can be compensated by this F multi. But as I said, I'm self-calibrating F multi, so it's not an issue.
Okay, thank you very much. Do you have an urgent question? Okay, urgent question is over there.
So I guess if you take this Mount theory outside about 0.1 parsec, that the Newtonian constant should be about 4.4 times.
Not outside 1 parsec.
Then
Outside.
it comes back to the original Newtonian constant. I mean, if it's outside the transition region, you said
Yeah.
it's about 1.4 times.
Yeah.
What about 1 parsec or 10 parsec, 2 parsec scale?
It will be the same in the Milky Way,
Right.
because in Milky Way all binaries are under the gravitational field of the Milky Way, so it will be the same. So outside these transition ranges, it will be it will be the same.
Bigger G constant.
Yeah. Bigger distance constant. But if it is in close sense, then the accelerations can be also contributed by other things, then it will be different.
Okay, given the time, we have to close here and make way for the next plenary talk. So thank you very much again, Kyu-Hyun, and thanks everyone for your attention.